In this video, we are going to talk about the limitations of the first law of thermodynamics. So far, we talked about the first law of thermodynamics and its various implications. In this video, we talk about why there is a need for a second law of thermodynamics. So therefore, we are talking about here the limitations. Okay, the first important limitation that we need to know that the first law is not able to predict the direction of the process. Okay, any process. Okay, be it a movement of heat from a hotter body to a colder body, or movement of a gas from a high pressure region to a lower pressure region. The first law doesn't talk the direction in which these processes should happen. For example, we know that heat transfer from a hotter body to a colder body, but first law doesn't say that it will transfer from a hotter body to a colder body. That means it is predict whether heat will flow in this direction or in the reverse direction. In the same manner, it doesn't predict whether gas will flow from a high pressure region to a low pressure region or a low pressure region to a high pressure. The direction it's not able to predict. Second important thing is it's not able to predict the possibility of an energy conversion. We know from natural observation that heat travels from a hotter body to a colder body. Okay, so this is a natural possibility. But first law doesn't talk about this possibility that heat will travel from a hotter body to a colder body. Okay, so it doesn't say the feasibility whether this reaction will happen or not. Okay, these are some of the natural process that we are knowing. Suppose we have another process which we don't know the natural urge. So thermodynamics should be able to tell me whether this reaction will happen or not. For example, if I talk about any hypothetical reaction like A plus B, giving you some reaction C plus D. Okay, I'm not talking here in terms of energy, but in terms of a reaction, because thermodynamics is valid also for chemical reaction. So if I talk in terms of a reaction, a new reaction, some reactant A and B reacting to K, C, and D. Thermodynamics should be able to tell me whether this reaction will happen or not. But first law doesn't talk anything about the possibility or the feasibility. Another terminology that we often use for feasibility, possibility is the term called feasibility. Okay, whether this reaction is possible or not. Okay, so this is in terms of reaction. Even energy, this reaction, even though we know that it is traveling from a hotter body to colder body, but thermodynamics is not able to, first law doesn't say, it tells that heat will travel from one body to another. That means energy can be transferred from one body to another or converted from one form to another. But it doesn't talk anything about whether this conversion will happen or not. So no indication of the possibility. Third limitation is it's not able to predict the extent to which this conversion happens. That means if the heat is okay, if heat is going from a hotter body to colder body, this heat transfer will happen till what time or to what extent? That is not predicted by the first law of thermodynamics. Then the fourth limitation is it rules out the existence of 100% efficient engine. We know that no engine is 100% efficient, but first law doesn't rule out this criteria. It says that if energy is converted from one form to another, it's always 100% conversions. For example, when we talk about automobiles where heat energy is converted to mechanical energy, it says that that conversion is 100%. We know that no engine is able to achieve a 100% conversion of heat to mechanical energy. But first law doesn't rule out this criteria. First law says that it is possible to make a 100% efficient engine. So that means these limitations, first law is not able to explain. Okay, so that is why we needed another law, and that's how second law of thermodynamics was was stated. Okay, before I go into the statement of the second law of thermodynamics, I would like to talk about a certain new type of processes which I did not discuss previously. One of this process is the spontaneous process. Okay, what is a spontaneous process? A process that has a natural urge to take place by itself under a given set of conditions. So that means all the natural processes, or those processes which we know by common observations that it will happen in this direction, those processes are referred to as the spontaneous process, or an other name that we give is natural process. For example, the heat flow from a hotter body to a colder body is a natural process or a spontaneous process. Similarly, a gas flowing from a high pressure region to a lower pressure region is a spontaneous process or is a natural process. So such processes which have a natural urge to go in a particular direction, those processes are referred to as the spontaneous process. An important what characteristic of a spontaneous process is that the spontaneous process cannot be reversed. You cannot reverse these processes. That means heat will travel from a hotter body to a colder body. That is, we know it is a spontaneous process, but the reverse, that is heat going from a colder body to a hotter body, is not possible. So these processes are irreversible in nature. That means spontaneous processes are irreversible. Okay, and if you want to do any kind of, like, if you want to transfer heat from a colder body to a hotter body, you need to do some kind of external work. Okay, only then you can do it. For example, more better you can realize it. If you want to make the gas flow from a low pressure region to high pressure region, you have to do an outside work in order to push the gas to a high pressure region. Okay, so without an external work, you cannot do a spontaneous process in the reverse direction. Okay, therefore, spontaneous process, or in other words, natural processes, they are irreversible process. Okay, now opposite a process of spontaneous processes, non-spontaneous process. Definition would be simply opposite. It's a process that do not have a natural urge to take place by itself under a given set of conditions. So those which are non-natural process, this doesn't have a natural urge to take place by itself. That means a non-spontaneous process will not happen by itself, but rather it requires an external work to happen. For example, if you want to make the gas flow from a low pressure region to high pressure region, that is a non-spontaneous process. If you want to make that happen, you need to do some kind of external work. Okay, so these are some of the processes that you need to be aware of. Okay, now coming to the important limitation that we talked about, that is the possibility of a energy conversion. That means feasibility of a energy conversion. Okay, so what are the factors that are responsible, or the criteria that is responsible for the feasibility of a process or a reaction? So another terminology for feasibility is spontaneity. Okay, you should be aware of all these terminologies. Okay, so what are all the criteria? Like, what decides whether a reaction will happen or whether this process will happen in this direction? Or in other words, what is the criteria that decides whether it is a natural process or not? Okay, so what are the criteria? So first important criteria that was used was the tendency of a system to acquire minimum energy, a state of minimum energy. Okay, this was one of the criteria. That means if a process is happening spontaneously, that means that system is able to achieve a minimum energy. For example, let us look into the example that we are so much looking into. You can see here, hotter body. Hotter body is at a higher energy. So when the heat transfer happens, that means this reaction is feasible. Okay, that is heat transfer from a hotter body to a colder body is a feasible reaction. Now, why it is feasible reaction? Because when this happens, when heat transfer happens from hot body to a colder body, the system is having attaining a minimum energy because it is releasing heat and therefore having uh, 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 having acquired a lower energy. Okay, so that is one criteria for the deciding whether the process or reaction is feasible or is spontaneous or not. Okay, but this is not a very uh, hard and fast or I mean say sufficient condition or criteria to decide whether a process or a reaction is feasible or not. That is because many reactions are known where the system does not release energy but rather absorbs energy but still are feasible. Okay, so that means this alone cannot be a good criteria. So therefore another criteria was brought in, and that is that criteria is the tendency for a system to acquire a state of maximum disorder. So that means the system usually try to go to a state of maximum disorder. Okay, for example, to understand this, let us look at this particular example here. Here you can see I have denoted two different gases with two different color. They are separated by a semi-permeable compartment. Okay, now when I remove this semi-permeable compartment, what I see is these two gases get intermixed or disorderly mixed together. Okay, this is a very feasible reaction. This is a feasible reaction because when I remove it, this will always happen in this direction. It is going from an ordered state where the two gases are separate to a disordered state. So that means this could be one criteria that would help me to understand whether this reaction or process is spontaneous. That is, it will try to achieve a maximum disorder. And how do we measure this disorder in a system? And for that, we use a quantity called entropy. Entropy is actually a measure of disorder or randomness in a system. Entropy is denoted by a letter, capital S. Okay. Capital S is the letter that we use to denote the entropy. Okay. Now, how is it mathematically related to quantifiable terms? Here we see a differential form of the expression here. This is the differential form of the expression which relates the entropy. So this is the differential form. We have no derivation for this expression in your course, so we are not doing it. So differential form of this expression. You can see here the infinitesimal change in the entropy is related to heat and temperature in this particular format. Now, the note you have to note here one important point, and that is heat here that is used is for a reversible process. It is very important that you can use this relationship only when the process that you are doing is reversible. If the process you are doing is not reversible, you cannot use this particular expression. Okay, so this expression is valid only when you are calculating the heat for a reversible process. Okay, and if your process is reversible and you're able to calculate the heat, this is how they are related to each other. So this is the differential form. If you want to calculate the finite change, as we did in the previous classes, we simply integrate both sides. When you integrate it from an initial state to a final state, we know that exact differential, when you do the integration, it will come as a the same function, that is entropy. Okay, and then that you integrate over initial and final function, and simply it is SF minus SI because this is a state function. However, when it comes to heat, it is not a state function. Now T, you can take it out, so that is why I have taken it out, because it's a constant term. Now heat in this particular format, you cannot integrate in the Normet format because it's a inexact differential. അതുകൊണ്ട് തന്നെ this would can be taken out as a total heat that is released. You simply replace this integral symbol with simple Q, reversible. Okay, so this is the expression that relates the change in entropy to heat and temperature. This is the mathematical form of the second law. So though I have not stated the second law, this is the mathematical form of the second law. This is the differential form, and this is the normal form that relates the change in entropy to the heat and temperature. These relationships you should always keep in mind. Now quickly, if I talk about the values of entropy between different phases, we know that highest disorder you will find in gases, and therefore the value of entropy of gases should be higher than the liquid. Solid, the disorderliness is lesser, and therefore entropy value also should be correspondingly lesser in magnitude. Okay. Now, in terms of unit, it is very simple to calculate the change in entropy's unit. It's simply heat is in joules, T is in Kelvin, so unit should be joule per Kelvin. Okay, so in the next video, we will talk about the statement of the second law of thermodynamics. Thank you. Have a nice day.